Okay, now we're going to discuss the cytoskeleton, the skeleton within the cell. Now, the cytoskeleton is obviously not bone. They are actually proteins, but they do what bone does in your body. One of the things is to hold shape. So the cytoskeleton is a network of protein fibers extending throughout the cytoplasm. There are three types of cytoskeletal structures: the microtubules, the microfilaments, and the intermediate filaments. The microtubules, the microfilaments, and the intermediate filaments. And primarily they differ in diameter. As we will see. Okay. Here is an electron micrograph of a cell. Now, you could not see this under the light microscope. Under the light microscope, you'd see none of this because they're too small. But these little things in the cytoplasm, remember, think about it this. Think of a balloon with jello in it, If you put the balloon down, it would flatten out. The cell doesn't. Why? Because in the cell, which they used to not be able to see before the electron microscope, you have all these structures here that pervade all through the cell and hold the cell shape. Microtubules, microfilaments that you could not see under the light microscope because you couldn't see that small. Okay? The cytoskeleton, microtubules, 25 nanometers. Microfilaments, 7. So the microfilaments are the smallest, micro. Then intermediate next, 8 to 12 nanometers. And then the microtubules, which are little tubes, are 25 nanometers. Here's some pictures of them and some things you can see. The microfilaments primarily are made up of a protein called actin. Actin is a protein that can contract. It's in almost all cells, but really where it does a lot is in muscle. But it is involved in changing cell shape because it can contract, which also helps in cell motility. It also helps in endocytosis. Remember, bringing stuff in, exocytosis, it can change this. And it also is going to help in mitosis, cell division. They're solid, 7 nanometers. It looks like it's made up of these little marbles called G-actin. Then you polymerize, hook them together, and get F-actin, which we'll talk about in muscle. And then you take 2 of these deals, which looks like 2 pearl necklaces wrapped around, and that's actin. So the little marbles are G-actin. Then you hook the marbles up to get a filament, that's F. And then you take 2 of these and you got actin. And this has contractile ability. As you can see. So you can here's the actin. Now in muscle, you hook it to myosin in addition to actin, and this is where the contraction comes. We'll talk about that later. Here's looking at muscle. Intermediate filaments is almost the most permanent. Almost all cells have intermediate filaments. They range between 8 to 12 nanometers because there are different kinds of intermediate filaments. The nucleolamins, vermentin, there are various kinds. Therefore, that's why they range between 8 and 12, but they're the most permanent fixtures of the cytoskeleton. Okay? They're rope-like proteins. That you can see here. That would be keratin is one type of intermediate filament. There they are there. Again, you can see. Okay. Then we come to the microtubules. The microtubules basically are hollow rods. What you have is you take these tubulins, these balls are called tubulins, and you wrap them around, and you have a hole in the middle, and then this diameter. You wrap a certain number around, a a certain number around, which means 25 nanometers is the diameter of this always. It's made up of tubulins. And they do a lot of stuff. They help with cell shape, change cell shape, radiate from the centrosome we'll look at real quickly. Here are the microtubules again. Now, here are special usages of the cytoskeleton. The centrioles, basal body, and what I'm going to call my cell appendages. All right, let's go to it. The centrosome. In a cell, you have something close to the center. Some means body, close to the center, and it's near the nucleus. From there radiates out a bunch of microtubules towards the cell membrane that helps hold the cell in shape. So but the main job of the centrosome is to help in mitosis. Now the centrosome was able to be seen somewhat with the light microscope. But when they got the electron microscope, they realized, and even with better light microscopes, they realized that the centrosome really was not one thing. They just couldn't see it. It's made up of 2 centrioles. Each centriole is made up of a bunch of microtubules. Again, the job of the centrosome is to act as like on your bicycle, to act as the spoke, and everything radiates out from there to hold the cell shape. But it also is important, as you'll see in mitosis when we talk about it. Now, cellular extensions, microvilli, little fingers. On top of certain cells, particularly epithelial cells we'll talk about, you can have these little projections. Mike, what's the purpose of these little projections? To increase surface area of the cell. Where's a good spot to find that? In the intestine, because this increased surface area would help with absorption of your nutrients. Now, what holds the little fingers up? Now, surrounding, I'll call it the skin of the fingers, shall I say, which is the cell membrane. But what holds just like your fingers, what are the bones, the phalanx in there? Well, it's actin filaments. Actin filaments form the core of this to keep them standing up. Okay? So here we are, microvillus, looking in. This would be a transmission electron microscope. See there? Okay. Cilia and flagella. Cilia's job is to move stuff over the top of the cell, like mucus. Flagella moves the cell. The only flagella really in the human is going to be that of the sperm, to move the sperm along. The inside, to make them rigid, are microtubules. So here would be, right here, a cilia, which would be a cilium, since it's just one. And inside there are microtubules in a certain pattern. Now, in addition to that, you have these dynein proteins. The dynein proteins help the microtubules move. Key to dynein proteins, it helps so you can sweep. It's like a broom sweeping. Now, let me tell you something. In your trachea, you have these. Okay, the trachea sweeps mucus up so you can spit it out or swallow it, and debris in there. You're constantly doing that. Nicotine, when you smoke, paralyzes the dynein protein, which paralyzes the cilia. That's why a chronic person smokes a lot, has to clear it themselves. You hear them do this. They have to constantly do that. But the core of cilia, job of cilia to move stuff over the cell, are microtubules. Okay? Microtubules. The flagella also has microtubules, and its job is to move the cell itself. These would be sperm. This would be sperm. Okay? Here you're looking at cilia with this power stroke, just like if you're using a broom. Power stroke, bring it back, recover. Power stroke, bring it back and recovery. See, with the cilia, with the flagella, I don't know how many you swim, you use your feet, your legs, in American crawl to rudder. So you have to power in both directions. If you sweep it, you only power in one direction, then you recover. But in both cases, these are using microtubules as the center. I already talked about the dining proteins, so we won't get heavy into that anymore. I'll move on. I'm not going to get into the pseudopodia. Okay. I'm not going to get into that. Now, the extracellular matrix, I'll just mention, is that which is outside the cell. That would be your fluids outside the cell. That would be your extracellular matrix. And we already talked about genomic equivalents. So with that, I'm going to close this. Oh, I have one more. Sorry. Theories of aging. Aging, there are many reasons for aging. Cells will only divide so many times. Well, I take that back. Cancer cells can divide indefinitely. Hey, let me say that statement again. Cancer cells can divide indefinitely. They have immortality. They can repair. The only way you can get rid of cancer is to cut off the oxygen supply to it or cut it out. But the normal cell will only divide a certain number of times. Now, there are many reasons. One is the DNA cuts off at the end until finally you don't have much. That's called the telomeres. The other is free radical. The other is autoimmune activities may occur. So there are many reasons for why we can only live so long and cells can, but these are all theories, of course. All right, with that, I will close this out and do another on mitosis, meiosis,